This video is supplementing another video that was on moments of inertia. This one's just going to go through the moments of inertia for not just a disc, but if you could remove a hole from the disc so you had a thicker ring, and then also the moment of inertia of the cylinder. So that's thinking of a disc, but actually a disc with a length of volume to it. And then I'll talk about the parallel axis theorem and the perpendicular axis theorem. To start off then, the moment of inertia of a thick ring, what I'm suggesting is that if you had a disc, okay, and before what we did to calculate the moment of inertia of this disc of radius r and mass m, just to remind ourselves, the moment of inertia of a disc is half m, the mass of the disc, times r, the radius of the disc squared. What we did was we looked at finding a small amount of mass, okay, in terms of a very, very thin slice. Okay, and we looked at this thin slice being a distance r away, and then what we did was we integrated from 0 up to r, adding up all these masses, okay, as we went from a certain distance up to the radius. The thickness of this disc, so the thickness of that disc was delta r, and so what we did was we found the mass of this in comparison to the mass of the overall object, and then we got an expression which gave us in terms of its radius, and then we integrated from 0 to r, and then we got this. Now what I'm talking about is what would happen if it wasn't a full disc, but actually part of that disc was missing. So it was actually a ring of thickness from here to here. And in this case, you've got two radii. You've got radius 2 to the outer part of the ring, and then you've got radius 1 to the inner part of the ring. But what we're going to do is the same as before. We're going to say that the mass of that in comparison to the overall mass of the ring is equivalent to comparing the area for the little mass to the area of the overall ring. Now the area of the little ring would be if we could work out the area of a larger part, the outer circle, and take away the inner circle, and we'd be left with this little thin ring. So the outer circle would be pi r plus delta r. Okay, square that, and then we would take away the inner part, which would be pi little r squared. And then before, the overall disk was just pi r squared, but this time it's going to be pi r2 squared minus pi r1 squared. So we work out the area of the large circle minus the smaller circle, we get the area of that thick ring. So pi r2 squared minus pi r1 squared. This is exactly what we've done before. This term was just pi r squared, okay? And what we'll do at the end, we'll see that what would happen if r1 was 0 and r2 was just r, so we were integrating not from here to here, but actually from the center out. And you should get back to this expression, okay? So what we're doing is we're coming up with a new moment of inertia from going from any position r1 to r2, whereas this is a special case when you're going from 0 to r, and that's for the entire disc with no hole removed. Right, I can expand these brackets, cancel some terms, make this look a lot simpler. So pi cancels. I'm going to expand this, so I'll just write down here, this is going to equal r squared plus delta r squared, and we've talked about a very small r. Squaring that's going to become even smaller to the point where we're going to neglect it. We're going to suggest it's 0, and then we should have 2, so r times delta r, and another r times delta r is 2r delta r, and then we're going to take away r squared, so that's on the top, and on the bottom it's just r2 squared minus r1 squared. Okay, so r squared minus r squared, you're going to be left with 2r delta r over r2 squared minus r1 squared. And now if we multiply it by the mass, we have our expression for the small amount of mass that we're going to integrate from this point to this point, from R1 to R2. So the moment of inertia for the small amount of mass is mr squared, so a thin disc, a thin ring, and that is m is this times big M. So we've got 2 big M r delta r over r2 squared minus r1 squared times r squared. So r times r squared, r cubed, and now I have the expression here that I can then integrate across the entire disk with respects to this amount of inertia. And what I mean by that is that we're going to actually integrate, because we've now got our small amount of mass in terms of the radius. We're going to go integrate from R1 to R2 this expression 2m r cubed dr over r2 squared minus r1 squared. And there are constants in here. The mass is not going to change. The inner radius and the outer radius of the shape is not going to change. So what I can simplify this down to is that the moment of inertia is simply going to be twice the mass of the thick ring divided by its outer radius squared minus its inner radius squared, and then multiply that by this integration, r cubed dr. So this is pretty much what we've done before, except for before it was from 0 to r, because we were going from the center of the disk out, because we were looking at the moment of inertia of a disk, and this was just r. Right, so integrating this, so we've got this, r squared, r1 squared, and that is going to be r to the power 4 divided by 4 between these values. That's going to give us 2m over r squared minus r1 squared, r2 to the power 4 over 4 minus r1 to the power of 4 over 4. And pull out a quarter, and then 2 divided by 4 is going to give me a half m. And then what we've got is we've got r squared to the power 4, r2 to the power 4, 2 being the second value to the outer ring, and then r1 to the power 4, and that's all divided by r2 to the squared minus r1 squared. And we're not quite finished, because this can be simplified, because if you think about what r2 to the power 4 minus r1 to the power 4 can become, we can actually suggest you can get this by doing r2 squared minus r1 squared multiplying by r2 squared plus r1 squared. Okay, so if I do r2 squared times r2 squared, I'm going to get r2 to the power 4 minus r1 squared times plus r1 squared is going to give me minus r1 to the power 4, and then r2 squared times r1 squared is going to give me plus r2 squared r1 squared, but then I'm going to also have a minus r2 r1 squared. And so we're going to be left with this. So this thing can be written like this. So I can actually say that half m r2 squared minus r1 squared times r2 squared plus r1 squared divided by r2 squared minus r1 squared. And here I can cancel these terms, and what I'm finally left with is that the moment of inertia of this ring, but this thicker ring, it's like a disc with a disc removed and inner disc removed, is actually equal to half mass r2 squared minus plus r1 squared. And as I said at the start, we can simplify this down to here, because if we suggest that r1 was 0, so we're starting from the center going all the way to r2 being the radius of our disk, if I replace that with 0 and that with r, I'm just going to get out half mr squared. Okay. Right. Next thing to discuss, just briefly, is just a cylinder. So if you think about having a disc, but a disc of some depth L, some length to it. So we know what the moment of inertia should be for a disc spinning about the rotation of axis through its centre. So that's just I equals half mr squared. But now, what would happen if you had a thickness to this? Okay, this length. Well, if you think about the volume of the cylinder, that's going to be the cross-sectional area times the length. Okay, and we could just go through the same process as before, finding a small amount of mass, but that would then have a length to it. Okay, and so if we were going to compare, like before, the area of the small amount of mass to the area of the whole mass, well, we can do that for volume as well. So we can actually say for a cylinder, we can compare the volume of that inner ring of mass to the volume of the whole cylinder. And using this expression, what we've got is the area, the cross-sectional area, times the length, divided by the cross-sectional area for the large cylinder times the length, and the lengths just cancel. And what we're going to end up doing is just the exact same expression for comparing areas, and then we'll integrate that and we'll get back to this. So actually the moment of inertia through the center of rotation for a cylinder is just the same. And likewise for the last example of a thicker ring with a section missing, it's just going to come out the same because of this. Okay, that was just something quick to talk about. And then I want to talk about what's called the parallel axis theorem. Okay, what this is suggesting is that if you had something where it could rotate about its center of mass, okay, so let's just say the center of mass is here, and then you wanted to shift the point where it's rotating, but it's shifted parallel to the axis of rotation for the center of mass. If you knew how far away that was, then what you could say is the new moment of inertia to rotate it about this point would simply be the moment of inertia for the object through its center of mass, rotating through its center of mass, plus the mass of that object, so this object has mass, times how much you've shifted the point, the axis where you're going to rotate around, squared. Okay, so this is what the parallel axis theorem is, but I'm going to kind of derive that with just a simple example of thinking about 2 point masses. So if we've got point mass 1, point mass 2, okay, and depending on, so if this was the larger mass, the center of mass between these two would be closer to this, or if this was the larger one, then it would be closer to that, further away from here. But at some point in between these, there's going to be a center of mass, and that object could rotate about that, and then we could find the moment of inertia about that point, about that axis of rotation. And so we would have a distance mass 1 is from that center, which I'm going to call RC for center of mass, R1, and then this is going to be the distance that mass 2 is away from the center. I'll just call it C2. Okay, and so if we were to do that, the center of mass, the moment of inertia about the center of mass would just be M1 RC1 squared plus M2 RC2 squared. Okay, but what we've suggested is we could shift the position where we're going to rotate about, and that's going to be shifted by a distance d. Now at this point mass 1 will be a distance r1 away. So notice r1's any value, rc1 is the distance to the center of mass, and then likewise m2 is now going to be a distance r2 from the center. So if I'm going to work out the moment of inertia now, I would just do mass 1 times r1 squared, that's how far away it is from the axis of rotation, plus m2 r2 squared. Okay, but now what I can do is I can say r1 and r2 in terms of their initial distance to the center of mass and this value d, how it's been shifted. And you can see that R1 would be RC1 minus d, and R2 would be RC2 plus d. Okay, and this would work if d went this way. Okay, I'll show you at the end about that, but for now I'm just saying d's going this way. So what I've got is that R1 is actually equal to RC1 minus d, and R2 is equal to RC2 plus d. So instead of having R1 and R2, I'm going to replace it with their distances to the centre of mass and this new distance that it's been shifted by the axis of rotation. So I get M1 RC1 minus d all squared plus M2 RC2 plus d all squared. If I expand out the brackets, M1 RC1 squared plus d squared, and then that would be minus 2 RC1d, so that would all be multiplied by M1, plus M2 would be RC2 squared plus d squared plus 2 RC2d. Okay, and then if I multiply out the masses, I'll get M1 RC1 squared plus M1 d squared minus 2 M1 RC1d plus M2 times RC2 squared plus M2d squared, and then finally plus 2 M2 RC2d. Okay, looks a bit messy, but let's collect things that are similar. So if I collect the masses times their distances to the centre of rotation, centre of mass, I'm going to have M1 RC1 squared plus M2 RC2 squared. I'll just cross them out to show that I've placed those here. Now this is originally the moment of inertia about the centre of mass of the object. And then I can collect these d squared terms. So I've got plus M1 d squared plus M2 d squared. And if you notice, that would be M1 plus M2 times d squared. And M1 and M2 is just the overall mass. Okay, so I could just call that md squared. And then I've finally got this and this term. Okay, so I've finally got a minus 2m1 rc1d plus 2m2 rc2d. Now, interestingly enough, this should disappear, because if you think when something is balanced, it means the moments are balanced, and the moments would be the force acting a distance away and the force acting a distance away. But if I think about that just sat there, the actual weight of the object is mass times gravity, and this side's the weight of the object, mass times gravity. So we can actually, instead of saying force times distance, just put it in terms of m1 rc1 equals m2 rc2. Okay, so that can only happen when you're kind of thinking about the distances to the center of mass, and that will be balanced. What that means then is if I have m2 rc2 and I take away m1 rc1, so m2 rc2 minus m1 rc1, I'm going to be left with, on this side, because I've taken that away, 0. And if we go back to this, here the like terms are 2 and d, so here I've got 2d times m2 rc2 minus m1 rc1. And I've just said that that would give me 0. So 2d times 0 is 0. So what you're left with is the moment of inertia of this, now that it's being shifted so it rotates about a new rotational axis, is the moment of inertia initially of the object around its centre of mass, plus the mass of the object times d squared. And as I said, if d was this way, that would just be plus and that would be minus, but you'd be left here with a plus and a minus, and then that would just be that takeaway. That is still going to give you 0. Okay, so that's the parallel axis theorem. And then the final thing to discuss is the perpendicular axis theorem. So the perpendicular axis theorem let's just think about a disc. We can rotate that disc about this axis in the Z coordinate. There would also be an X and Y coordinate. So you could rotate it about Y, you could rotate it about X, okay? And then this thing, if we were going to work out, so we've got a small amount of mass, dm, and then we know how far away dm is. And if we were going to work out the moment of inertia of this entire shape in the Z direction, we would just simply be summing up all the masses by multiplying it by every single distance squared with respect to the mass, okay? But if you look, this R on this plane, this XY plane, that's going to tell us, if you look at this, X, Y, and R is linked, okay? So X and Y, this is a right angled triangle, and so R squared would equal X squared plus Y squared. So if I replace this, I've got X squared plus Y squared, dm. And then what I'm suggesting then is I'm just going to be integrating the X squared and separately the Y squared. And then what you're left with is this is actually the moment of inertia for rotating about X, and the moment of inertia for rotating about Y. And so what we've actually found is that the moment of inertia in the X coordinate is equal to the moment of inertia in the Z coordinate is equal to the moment of inertia in the X plus the moment of inertia in the Y coordinate. Okay, and this is what's known as the perpendicular axis theorem. And yes, I've kind of done that very quickly and just in a brief way with a very simple example, just like I did with the 2 point masses, but that theorem does work for any shape.